And share screen. Oh. Share screen, voila. Okay, screen sharing. Let me. Voila. Okay, so I can't see anybody anymore. If you have any questions, just chat at me. Okay, so I'm guessing you know this already. My name is Peter Latham. I'll be teaching the next 12 lectures if all goes well. Email is PEL. What's happening here? Hold on. Are more people joining? Is that what's happening? No. Okay. Although I believe you have that information already. Okay, more people are joining. Okay, so before I start with my section, I'm going to give a little bit of a big picture view. So what do neuroscientists do and why? So this is your brain. So into the brain gets input, so sensory input. So vision, audition, what you see, what you smell, what you hear, and the output is basically movement, so it's motor. So input is sort of information about the world, output is moving your muscles. Pretty straightforward in principle. And so in some sense, what neuroscientists want to figure out is how do neurons implement this transformation? This transformation. This is a goal of neuroscience, because remember, inside your brain, you have, the brain is just a bunch of neurons. That's all you have. Now, humans have about 100 billion. Other animals have fewer. They're connected. They receive sensory input. Okay. Okay. They receive feedback. So these neurons receive sensory input. They eventually produce drive muscles. And this question, how, nobody really knows what that means. So for man-made devices, how is usually pretty easy because things are highly modular. Pretty much anything we make, we design one piece, we design another piece, we put them together. You can think of any sort of complicated objects, cars, toasters, computers even, anything. It's, we design one piece at a time, we put it together in a sensible way. The brain is very, very highly distributed. I'm guessing you guys have learned that if you look inside your brain, you have, this is your brain. You have visual areas. Vision, vision is, the textbook story says vision is done in one place. Motor is done somewhere else. So the textbook version, your brain is kind of modular. That's not actually what's really going on, okay? If you look, for instance, in the visual system, you'll see every time you move, your visual system. So if you move, when you move, neurons in your visual system are active. Okay, so it's not really as simple as the brain is divided neatly into multiple parts. Sorry, question. Okay, so that's why everybody's logging in. That's totally fine. Okay, so the brain, this how question is pretty complicated. So the conventional wisdom, sort of the simplified version of how goes, the story goes something like this. So your brain's full of neurons. I draw a neuron like this. So if you remember from the course, you've seen this already. You have a soma. You have dendrites, and then, so dendrites. And then here's an axons. And the neuron spikes, you spikes travel down the axon to the next neuron. And so the connections there are right here. And we can write down equations describing these neurons. I'm going to actually write down a linear integrated firing model, which I've assume you've more or less seen. So if the voltage on neuron I is VI, so VI is, so this is voltage on neuron I. So these equations I can write down are basically central to the next two lectures. If you have any questions about these, let me know. So, oops. VI minus E leak. This is a linear integrate and fire model. In the absence of inputs, the voltage relaxes toward the E leak voltage, which is around minus 65 millivolts. Okay, and then it also gets other synaptic input. Sum on J. This is all a neurons do. Wij, Gj of t. So Vi minus Ej. And so sum over J. This is the sum over J is sum over J refers to other neurons. So this is input from other neurons. other neurons. So I assume this is mainly review. Okay. This is a very simplified version of the brain. And then what happens is when VI, oops. So VI is greater than about, let's say, VTH is about minus 50 millivolts. Neuron spikes. And the GJ here, these terms, the GJ, sort of the result of a spike. So GJ of T looks like this versus time. This is time. This is 0. So basically, if these are the spike times when neuron J spikes. So what happens is GJ jumps up a little bit, and it decays down, jumps up, decays down, jumps up, decays down. Okay. So this is an approximate model of neurons. It's a pretty simplified version. I don't know if you heard about the dendrites can do complicated processing. There can be delays, but this is not a bad model of what's going on in the brain. And it's kind of important you understand it, okay? So this reversal potential, so the EJ, this term here, we're going to talk about that a little more in a second, but that tells you whether the neuron's excitatory or inhibitory. So basically the voltage gets pulled toward EJ. So if excitatory neurons, EJ, the reversal potential is around 0 millivolts, so it gets pulled up. Inhibitory neurons, it gets pulled down. Okay. So this is the basic model of the neurons on short time scales. So tau, if you recall, tau is about 10 milliseconds. Okay. So in some sense, for the next couple lectures, we'll be studying this set of equations. And we'll be studying it. So in reality, what happens, the way you learn is the weights change. So learning weights change. So the weights themselves undergo some equation, tau W, dWij dt equals, it's not really known. We know something about plasticity, but we don't really know how the weights are updated, okay? If we did, we'd have a full set of equations. We'd have a set of equations describing, can you see the little hand there? I hope so. You said equations describing neurons on short time scales, and we have a set of equations describing learning. And in principle, if we had those equations, we could figure out how the brain does what it does. A note of caution, we probably can't. The equations are going to be incredibly complicated, as you said. As I said, the human brain has about 100 billion neurons. Even a mouse has about almost 1 billion. So there are a lot of equations, and learning rules are sort of complicated. But this is really our starting point for understanding the brain. When we say how, back to here, this question, how do neurons implement the transformation? To answer that, we have to know something about the neurons. Okay, So what I'm going to do, I'm going to talk about these equations in the next couple lectures. So and do it in stages. So we're going to first. So let's actually talk about what we're going to do. So what am I going to do in the next couple lectures? So first of all, oops. I'm just getting used to this. Okay. So stage one. So analyze networks of neurons before learning. So weights are random. Now, that may seem like a crazy thing to do. Randomly connected networks, you might think are really boring and interesting. It turns out they're complicated and they have all sorts of interesting dynamical structure to them. And the idea, at least in neuroscience, is what's happening is you start with the randomly connected weights, or not quite randomly connected, you evolve, but within a circuit kind of randomly connected, and learning happens on top of that. So in the second part, we're going to say, okay, we're going to add some structure to the weights. The weights. And I'm going to say, in some sense, we're going to add some particular structure that we know how to analyze, which is going to be, in some sense, we don't know how to analyze much, but there's some structure we know how to analyze, and that will give insight in the kind of things that networks of neurons can do. In part 3, we're going to consider plasticity. So weights change with learning. With learning. And this is going to be first facts about the brain. And then some deep learning. I mean, obviously, deep learning is a huge field right now, so we can only scratch the surface. And I'm going to try to focus on things that are relevant to the brain. And then in part 4, we'll do a little bit of, we'll totally switch gears in part 4 and talk about basically reinforcement learning. And the reason we kind of switch gears is because, oops. Is because for the first 3 topics, we'll actually be consider real neurons. Reinforcement learning will be at a much more abstract level. Okay, so before I start, there are a couple things that you guys, there's some math that you really need to know, because I'm going to be using it over and over again. So I'm going to put this here. I'm not sure quite what your math background is. I think it's relatively sophisticated, but these are the kind of things that I will be using a lot in these lectures. If you aren't able to deal with these equations, it's going to be quite tough. So you can email me or look things up. But anyhow, so first of all, sort of this linear one-dimensional equation you should be able to handle. The x dt equals minus kx plus c, where c is a constant. Can also depend on time, but it's a little bit harder. So you should know the solution to this differential equation. Differential equations always come with initial conditions. Let's say x of 0, t equals 0, equals x naught. And this has a solution, x of t is equal to c over k 1 minus e to the minus kt plus x naught e to the minus kt. Okay, so you should convince yourself that's correct. When t equals 0, you can see x of t equals x0. And then when t equals infinity, x of t equals c over k, as you can tell from here. When dx dt equals 0, x equals c over k. So that makes sense. You should convince yourself that that's correct. The other thing you need to know is basically Taylor expansions. And really, we're going to use Taylor expansions mainly for to analyze stability of fixed points. So let's say you had equation dx dt, x is a vector, dt equal to f of x. This is shorthand for dx I dt equals fi of x1, x2, all the x's. Okay. So vectors notation is super convenient. And then if you have the equation f of x0 equals 0 is a fixed point of that equation, right? When x equals x0, dx dt equals 0, and it stays there forever. But if you want to know what happens at near x equals x0, so you should be able to let x equals x0 plus delta x and expand. So x0 is a constant. So d delta x dt equals f of x0 plus delta x is approximately equal to f of x0 plus delta x dot partial with respect to x0 f of x0. Okay, and this, remember, f of x0, remember, is equal to 0. So this thing is equal to some matrix J dot delta x, where Jij is equal to partial of fi of x naught with respect to x0, the jth component of x0. Okay, so this is the equation you should be able to solve. It has a solution typically in almost all cases. So delta x is equal to the sum on k. Well, let's not do that. So what you really need to know is about what you really need to know about are eigenvalues and eigenvectors. So J has eigenvectors. So J dot vk equals lambda k vk. The lambda k are the eigenvectors. J has adjoint eigenvectors. Vk dagger dot j equals lambda k vk dagger. Okay, and it turns out that, except for pathological cases, vk and vk dagger can be chosen orthogonal. So vk dot vl dagger equals delta kl equals 1 if k equals l, and 0, k not equal. Okay. And when you do that, you can write delta x equals the sum on k of ak, vk. And if you plug this back in, you get ak dot, or dak dt equals lambda k. And ak equals vk dagger dot delta x at t equals 0. Okay. So these are the two sets of things you should know. I mean, in some sense, the first one is a linear equation. Oops. So the first one's a linear differential equation. The second one is we take a nonlinear equation in high dimensions and turn it into a linear differential equation. Okay. So you should definitely know 1 and 2. If you know them already, that's fine. If you don't, that's okay. And we're going to be using these things over and over and over again. Okay. Okay. So that's sort of warm up. Let's now actually start talking about some analysis. Remember, we're going to analyze this equation. I'm going to put a tilde over here for reasons you'll see in a second. So let's see, I should be able to cut and paste this. Cut and new page and paste. Voila. Okay. So this is going to be our equation that we're going to be studying for a while. So the first thing I'm going to do is simplify this a little bit. You'll notice I put a tilde. I put a tilde here over the W. And the reason I did this is called the conductance space model. So this is a conductance space model. Okay. So what we want to do, so this is sort of the picture we're going to have. So we have a whole network of neurons. Okay. So J is a sum which goes from 1 to n, where n is large. Although in a network of neurons, so you can have a large number of neurons, but they're not all connected. So we can think of this as a bunch of neurons. So you have a network of neurons. They're connected. You have some connections, but that's weird. Okay, things I've got out of order here. That's okay. I'll get it in order before I save it. They're connected. So each neuron gets input from many other neurons here, but not every one. So each neuron gets about k inputs. So it receives inputs from actually, well, 2k inputs, and k is around hang on. So K is about 1,000. So each neuron in this network can be a very large network, and can be, millions or hundreds of millions. But even so, each neuron gets input from only about 2,000 other neurons, and we'll see why that's due in a second. Okay. And what we want to understand first, so for our first question, so question number one is we want to draw, so our goal, for now find the firing rate of every neuron as a function sorry gang, this is a new program and I clearly don't really know how it works. As a function of the weights. Okay, so the deal is I tell you all these Wij tildes, and you tell me the firing rate of every single neuron in a network. It's kind of a hard problem. So we're going to say, we're going to do some things to simplify our lives. Let me see something. Okay. And simplification. So the first simplification is we're going to go. So one, we're going to go from a conductance-based model, which is kind of hard to deal with, but not impossible. And we're going to go from a conductance-based to what's called a current-based model. And to do that, what we're going to do is replace V. So replace V. So VI goes to VI bar equals constant. That's clearly not a great approximation, but it's not bad. And let me tell you why. So I sort of haven't drawn a picture. So with this model here, so this neuron here is getting it's this term is trying to push it back to the leak potential. This term here is basically some fluctuating drive from all the other neurons. Every time neuron J spikes, this neuron, the voltage gets a kick. And so what happens is if you plot voltage versus time, oops. Okay. If you plot voltage versus time, VI versus time, so here is our E leak. So E leak, approximately minus 65 millivolts. And then up here is E threshold. Remember, when the neuron hits threshold, it spikes. And so what happens is the voltage kind of wanders around here. Every now and then it emits a spike. I'm not showing how high it goes. Then it resets, it wanders around, it goes up here. Okay. So most of the time, the voltage is, besides these big spikes where the voltage goes up by a lot, around here, so the voltage doesn't vary. doesn't vary too much. Okay. It's mainly set, between minus 65 and, so this here is about minus 50. So, it varies with around 50 millivolts, but, given the approximation we make, it's not such a bad approximation. Just set that to a constant, okay? And when we do that, our equations become, let me chop this over and move it. Copy. And let's go to a new page. And paste it here. Okay. Oh, yeah, so this is constant. So this becomes VI bar. So this is constant now. And now we have two types of neurons, excitatory neurons. So neuron comes in mainly two flavors, excitatory neurons. So excitatory neurons. So EJ is approximately equal to minus or plus 20 millivolts. And inhibitory neurons, so EJ is approximately, minus 80 millivolts. Okay. And remember, so if you look at this, for excitatory neurons, the reversal potential is well above the threshold of plus 50. Inhibitory neurons, the reversal potential is well below threshold. So inhibitory neurons, the voltage gets pulled down away from threshold. Excitatory neurons gets pulled up. So we're going to make a definition. We're going to define take Wij tilde times and VI, and then I would do one more thing. And we'll set, for convenience, VI bar, let's say equals minus 65, somewhere around there. Okay. So now we define Wij tilde times E excitatory. So this is E excitatory. This is E inhibitory. Minus V bar. We define that to be Wij. And Wij tilde times VI bar minus E inhibitory. We're going to define this to be Wij, we'll call it E. Wij. Okay. And when we do that, our equations simplify. Let's go to blue. Our equations become tau dV dt equals minus VI minus E leak plus the sum on J of Wij E Gj of T and these are now excitatory neurons that are firing, minus the sum on J of Wij, Gji of T. Okay, so this is a set of equations we're going to work with. So we're going to focus on these equations. And given these equations, now we're going to ask what's the firing rate of every neuron in the network. The other approximation we're going to make is that neurons are randomly connected. So let me see, 11, 12. I'm going to go one more. I'm going to do one more thing, and then we'll take a break. And you guys can let this sort of let this sink in. So what I want to know is now, suppose I knew the firing rate of, so we're going to consider the following problem. So suppose I do not know what's going on here. 3 rearrange order. Okay, so problem. Let's use a better color. Okay, so suppose we knew the firing rates of all but one neuron. Okay, what's the firing rate of our remaining one neuron? Okay, so the picture is this. So this will sort of this neuron here is going to be our neuron of interest. So we know the firing rate of all the neurons that are going into this one. So we want to know what its firing rate is. Okay, and you can imagine if we do that, then we could write down a firing rate equation for every single neuron in the network. It would still be a lot of equations, but given those firing rates, we might be able to actually figure out the firing rate of every neuron. Okay. So we're going to go back to our equation here, and we're going to fix a firing rate of a bunch of neurons and ask what's the firing rate of. So if we fix a firing rate of all these neurons and sum over J, and that's the firing rate of our remaining neuron. Okay. I will actually get part way through that calculation. Okay, remember, let's actually be a little more clear about exactly what Gj of T is. So to do that, we need expression for Gj of T. Okay, so Gj of T equals the sum on K of some function. Actually, I use F way too often. Let's use a different symbol. We'll call it, I don't know, one runs to the symbol. H of T minus T JK. So TJK equals time of kth spike on neuron J. Okay, and H is just some function of time. So H of t looks like this. As a function of time, this is time, and this is 0, and it jumps up and comes down. Okay. Sometimes we have it rise instantaneously. It's 0 when t is less than 0. In real networks, this time for real neurons is somewhere between 2 to 10 milliseconds. Usually it can be longer for some neurons, but it's pretty fast. And so sometimes we even model as instantaneous rise. So we might also model it as h comes straight up and comes down. So in this model, h of t would be e to the minus t over tau s times step function of t. The step function of t just means 0, 0 for t less than 0, 1 for t greater than or equal to 0. Okay, and we want to normalize this, so we divide this by tau s. I'll tell you why in a second. Okay, and the reason we divide this, we're going to demand that the integral dt from 0 to infinity of h of t equals 1. So this is a very convenient normalization, and of course it's totally fine, right? Because if you look at here, oops. Okay. If you look, if you look down here, so we can always scale g by some factor and absorb that into the weights. Okay, so this is completely arbitrary, but it's very, very convenient. Okay. So I'm sorry about my ability here. Okay, so given that normalization, we're going to come back here, and what we're going to do is take these two terms, and we're going to average, we'll time average the right-hand side. The right-hand side. Okay. So let's just take about a 5-minute break. It's hard to sit still for an hour and a half. We'll take a 5-minute break. When I come back, we'll do the averaging. We'll figure out the firing rate. When sort of we'll answer our question is, suppose we know the firing rates of all but one neuron. What's the firing rate of our remaining one neuron? Okay. So let me just recap a little bit of what we've done before we take a break. Our starting point was this. I'm really sorry about this. Well, something always goes wrong. Our starting point was this equation here. So this is a okay. Our starting point was this equation here, which is a pretty good model of neurons. It's a linear integrate and fire neuron. Remember, it gets pulled toward the leak reversal potential of minus 65 millivolts. But if this term here, which comes from other neurons, causes our neuron to spike, causes the neuron to go above minus 50 millivolts, it emits a spike. When it emits a spike, it basically activates other neurons in the network via this GJ term, which is connected to lots of other weights. We made this is a conductance-based model. We turn this into a current-based model by setting VI to a constant, and that gave us equations like this. We define GJ as a little blip every time neuron J spikes, and we chose it so that it integrates to 1. And that'll be convenient in a second. And this is our picture of a neuron. This is a picture of a neuron down here. As it gets fluctuating input, when it hits minus 50 millivolts, it emits a spike and goes back down, and then fires fluctuates again. And these spikes are what causes our GJ of T to activate. Okay, so let's take a break. In the meantime, I'll figure out how to rearrange these things and hopefully make it work out. And I'll be back in 5 minutes. If you have any questions right now, put them in the chat, and I'll answer them.
你的要放快了。对。
You have water. More water. Okay.
What?
Okay, let's start up again. Okay, so I at least solve one problem. So remember our what we want to do. We want to basically, we know the firing rates of all the neurons in the network except for one. We want to find a firing rate of remaining one neuron. And what we're going to do is, and so this right-hand side, this sum over J is kind of interesting. It has some non-zero time average, well, these neurons, and on top of that has some fluctuations. So the first thing we can do is time average the right-hand side, and then use that to figure out the firing rate of the neuron, and we'll talk about what happens when we have fluctuations. Okay, so I'm just going to take one term here, the excitatory term, and time average it. Okay, time average it, and see what we get. That's actually relatively simple. So that's our next step. I'm going to add a page. So we want the time average. So we'll take sum on J. We want time average of sum on J, W I J E G J of T. Okay. The time average, we'll assume that the neuron is firing at a constant rate. So this is 1 over T, the integral from 0 to T of the sum on J of W I J E D J of T. And T is large. Okay. So the only thing that depends on time is GJ. So we just basically need this is equal to the sum on J, W I J E, actually an E here, excitatory neurons, of 1 over T, the integral from 0 to T, dt T J E of T. Oops. Okay, so let's consider this term here. I'm going to write this as, we'll give it definition, 1 over T, the integral from 0 to T, dt of the sum on K of, shoot, what did I use? H of t minus tjk. Okay. So remember the integral over h. Whenever there's a spike, so this is k equals to nj of t. So nj of t is a number of spikes we have between 0 and capital T. Okay. The integral over h is just 1 whenever there's a spike. So what this thing is equal to is n of t, nj of t, number of neurons that's fire in time j divided by t. And this is just equal to the firing rate of neuron j. Okay, so this is firing rate of neuron j. Okay. And you know, may have to think about that a little bit. It's because of our choice of this thing integrating to 1 was just convenient, and that made the firing rate. And either way, it just makes sense, right? The longer GJ of t, the higher the firing rate of the neuron, the bigger that's going to be. Okay. So the time average of this thing is basically the sum on j of wij nu j e. The firing rate of excitatory neuron E. Okay. So that's kind of nice. So we go back to here, and these averages. Let me cut and paste this thing. So I'll cut and paste this. Let's go down. I see what happens. Paste. Kill that. So the time average version of this, so when we time average, we get tau dvi dt is equal to minus vi minus e leak plus the sum on j of wij e nu j e minus the sum on j of wij nu ji. Okay, so we ignore temporal fluctuations, and now we get something quite simple. The higher the firing rate of the excitatory neurons, the more excitatory drive it gets, and the higher the rate of the inhibitory neurons, the more inhibitory drive it gets. Okay, and this is now an equation we can analyze for a linear integrated fire neuron, and we're going to do that in a second. But first, we're going to make sort of a rather strong approximation, and we're going to see later on this is not a bad approximation. The sum on j equals 1 to n of wij nu j e. So remember earlier, each neuron receives input from about k other neurons. Okay, and so we're going to make a strong approximation. We can think of approximation. So this thing is more or less equal to, so k, so this is number of connections, times we I'm going to give this a name, WETYP. That's a typical weight. Okay, that's typical weight if there's a connection strength times nu E bar. So this is the average. So this thing here is typical weight. And this is average excitatory firing rate. And in the next lecture, we'll make this a lot more rigorous. We'll see why this is an okay approximation for some things. And so remember, K is about 1,000. So it's kind of a big number, okay? So the first approximation was the time average. The second approximation was to not worry about, just set all the weights to about the same value, and we get an equation like this, okay? And so what it tells us is that our equation now becomes, now let's write it down again. Well, I can cut and paste. Okay. So actually, this maybe I shouldn't have bothered. And now we'll put a big approximation sign here. Approximately. Plus K. So WE typical, nu E minus K, WI typical, nu I. Okay. So, and then basically, so E leak, let's say E leak equals minus 65 millivolts, and E threshold equals minus 50 millivolts. Okay. And so what happens is, if the excitatory firing rate is high enough, the voltage as a function of time looks like this. So this is minus 65 here. This is minus 50. So it starts, let's say if it starts at minus 65, it gets pulled up here. It's minus 50, it generates a spike. And we'll say it resets. And we'll say it resets to, after a spike, so after a spike, resets to minus 65 millivolts. Okay. So here's the picture. We're driven by, because we've ignored temporal fluctuations, we're driven by a constant term. If this constant term is big enough, it causes the voltage to start at minus 65, go up to minus 50, spike, and come back down. So to compute the firing rates, we just need to know, this is, call this T spike. We need to compute that quantity, and then the firing rate of our neuron, nu, this is nu I, equals 1 over T spike. Okay. And that's what we're going to do next. We're going to do one more thing first. Actually, let's just do that now. Okay. So we can treat this term here as a constant. Call it C. Okay. We're going to fix the firing rate for treat as a constant and figure out how long it takes to go from -65 to -50, or E threshold to E leak. And that's a reasonably straightforward calculation. So our equation is tau dv I dt equals minus V minus E leak plus a constant. We'll work out in a second. Initial conditions are Vi of t equals 0 equals 0, equals E leak. And we want to know T spike. So T spike equals time to go to ETH. Okay. Okay, so let's actually make a change of variables. U equals Vi minus E leak. And our equation becomes tau du dt a better handwriting. So we have tau du dt equals minus U plus C. And this has the equation U of t. And remember now U of 0 equals 0. So basically, U is memory potential relative to -60. So it starts at 0 relative to -665, then moves up by 15 millivolts to spike. Okay. So U of t is equal to C times 1 minus E to the minus t over tau. Okay. So that's very easy to verify. First of all, we know when t goes to infinity, U has to equal C. Okay. When t goes to infinity, the neuron stop, du dt becomes 0, so U equals C. And that's what happens when t equals infinity. It's got its 1 e to the minus t over tau decay, and at t equals 0, U is 0. Okay. So T spike, so U of T spike is equal to E threshold minus E leak. We'll just call that delta E. And that's about 15 millivolts. So a neuron has to increase by 15 millivolts to spike. Okay. So we just basically plug that in here. We plug in 15 or delta E equals C e to the 1 minus e to the minus t over tau. Sorry, this is T spike divided by tau. Okay. So we saw that, divide both sides by C, subtract 1, and we get e to the minus T spike over tau is equal to 1 minus delta E over C. Okay. Now that's only true if C is beta. So this is C has got to be greater than delta E. If C is less than delta E, the neuron will never fire. Okay. Actually, not much greater than. greater than. It's got to be greater than delta E. Otherwise, the right left-hand side will be negative. Okay. Now we take the logs of both sides, and we get minus T spike is equal to tau log 1 minus delta E over C. And remember, firing rate nu for neuron I is equal to 1 over T spike. Is equal to 1 over tau, 1 over minus log 1 minus delta E over C. Okay. It's not a very intuitive expression, but we do know something. One thing we know is that tau, well, I know this, I haven't told you, tau is approximately equal to 10 milliseconds. Neurons have a very short memory. Tau is 10 milliseconds, so 1 over tau is actually approximately equal to, we'll just say equal to 10 milliseconds. Tau equals 10 milliseconds, pretty standard number for neurons. So 1 over tau equals 100 hertz. Okay. So basically, the right-hand side, the prefactor is 100 hertz. So the firing rate, as long as this number is greater than about 1, the firing rate is going to be huge. Neurons actually can't fire faster than 100 hertz. Okay. So the function of C, basically, if you plot the right-hand side as a function of, well, C over so on this axis, we'll put C over delta E. On this axis, we'll put nu I. And this is 1. So basically, if this is less than 1, C over delta E is less than 1, meaning 1 minus delta E over C is negative, nothing happens. Remember, we need to put it around here, down here. C has got to be greater than delta E, which means C over delta E has got to be greater than 1. But this rises really fast. Okay. So by the time this is 2, by the time it's E, or approximately E, so this sort of the scale of this is around here, is around 100 hertz. Okay. So in fact, at that point, this model breaks down because neurons typically don't fire faster than 100 hertz. Okay. So the point is, as a function of C, this thing rises very rapidly. The problem, of course, is we don't really know what C is. Okay, and that's because, where'd C go? C is over here. We don't really know. So right now, these weights have been very abstract. We don't know what they are. Okay, so we need to express the weights in terms of something we know about. And the one thing we do know about is, if you look at a neuron, so I'm going to put it right here. If you look at a neuron, if you patch a neuron, so it's got some dendrites. If you patch it and plot, so the voltage of the neuron, voltage as a function of time, it's getting with no much input, so -55. Let's say it's not getting input at all. And then at this time, so 1 presynaptic neuron fires. One presynaptic excitatory neuron fires. What happens? The memory jumps up and it goes back down. Okay, and this height, the height here is called, shoot. The height here is called this is called a V EPSP. So excitatory postsynaptic potential. Okay, and this is about, it varies, but on average, it's something like 0.5 millivolts. Okay, so we're going to use that fact to infer the weights. Okay, so we have to go back to our time-dependent equations. So right here, we're going to go back to these equations. I'm going to say the right-hand side is mainly zero except for a single neuron fires. Okay? And we're going to ask, in a single neuron fires, how big should the weight be to generate a PSP of about 0.5 millivolts? And that's going to tell us what our weights are. And then in turn, that's going to tell us what the C, this capital C is. Okay? So let's do that now. We write tau dvi dt equals minus vi minus e leak plus, we'll just have one weight, one excitatory weight, wij gj of t. We're going to solve this we're going to actually take a really simple case. Remember what gj of t looks like. So neuron, this is in the case where neuron spikes neuron J spikes once, only once at time t equals 0. Okay, so gj of t looks like this. So if this is 0, it's 0, and then it jumps up and comes down. And we're going to basically make this really fast. Which basically we're going to set it equal to, really fast means gj of t is equal to delta of t. So this is a direct delta function. And so this is you know about direct delta functions. The favorite function in the world, it just basically means it's really, really, it goes up. It basically means this time here goes to 0. And when it goes to 0, this gets, oops. When it goes to 0, this basically becomes very, very high. So it really comes way up and comes down. Okay. And when that happens, when we integrate delta V, this just basically, it just jumps. So if you don't know about delta functions, you should look them up. But the solution now to this equation is, so first of all, VI, let's go. So VI oops. So VI at t less than 0 t less than 0 equals E leak. And then Vi at t greater than 0, it just jumps up by 1 of t greater than 0. Or tau Vi is equal to E leak plus Wij. And basically, it's this fact that it's just little facts about delta function. If you have dx dt equals g of x plus, let's say, w delta t. Remember, the way we integrate things is x at t plus delta t equals x of t plus integral from t plus dt g of x of t. This is actually exact, plus w, the integral from t to t plus delta t of delta t prime dt prime. And this delta function, this delta function here integrates to 1, just like this g integrates to 1 whenever there's a spike. So when you integrate across this delta function, x jumps by the amount w. That's exactly what happened here. It jumped by the amount w, and so the height, and then actually after it jumps, it decays. It decays by away from the jump minus t over tau. Okay, so the picture then is gj of t looks like that, and we can now plot. We can plot. This is t equals 0. So gj looks like this. It goes up really fast and comes down. It basically goes up to infinity. So this is gj of t, and vi of t jumps up and comes down. This is minus 65. So the height of this thing is wij. That's the height. And what that means is that tau oops. Tau v EPSP equals wij. And remember, this is around 0.5 millivolts. Okay. So we're pretty much all set. We can now go back to so what this says is W typical, the typical size of a PSP. So let's actually just cut and paste this equation and move it over. Let's paste. There we go. Okay. So basically W WE typical is equal to tau V EPSP. And WI typical for the same arguments is equal to tau V IPSP. Okay, and I can actually give this a name. IPS and EPSPs are about the same size. But we're going to call this G. G times V EPSP. Okay. So this quantity here, which was C, so C is equal to K times tau times V EPSP times excitatory firing rate minus G times inhibitory firing. Okay, and if we go back to what we care about, which is delta E is, remember, delta E is V threshold minus V leak, oops. Okay, is E threshold, put this pen, E, my pen stopped working. Uh-oh. Ooh, can you guys still hear me? This thing froze. Uh-oh. Okay, we're at the end of the time anyway. So I'm going to save these lectures to save these notes to lecture. I've recorded the Zoom video. I will put that eventually on the website. Hopefully you're still here. Are you still here? Will somebody say something in case you're still here, because my laptop seems to have absolutely frozen. Shoot. Okay, it's working again. Oops. Stop share. Okay. Good. You seem to still be there. So I'm gonna, as I said, I'm gonna get the lectures in the right order.
Professor, I think you can stop here.
Yeah, I'll stop here. And we'll continue where we left off yeah, on Wednesday. Okay, thank you.